So the plan for the lecture today is the following. First of all, I will very briefly remind what we did last time. We introduced trace map, we studied dynamical properties of the trace map, we related those dynamical properties to the spectral properties of Fibonacci Hamiltonian. Then, as I promised, I will give several purely dynamical problems formulated in purely dynamical terms, open problems that have immediate relation to spectral properties of one-dimensional quasicrystals. Then we will introduce the notion of the density of states measure for one-dimensional quasicrystals. We will establish relation of that density of states measure with measure of maximum entropy for the trace map in the case of Fibonacci Hamiltonian, and deduce some list of properties. And finally, we will discuss that density of states measure can be actually defined for multidimensional, higher dimensional quasicrystals in a great generality. So that's the plan. Last time we introduced the trace map. This is this polynomial map in three-dimensional space, and it is related to the properties of one-dimensional Fibonacci quasicrystal in the following sense. Let's consider this line in three-dimensional space. This line is parameterized by the parameter E, energy. And for each point on this line, the corresponding energy, corresponding parameter belongs to the spectrum of the Fibonacci Hamiltonian if the positive semi-orbit of this point is bounded, and it doesn't belong to the spectrum if the positive semi-orbit is unbounded, and in this case, actually it must go to infinity. So in this way, you reformulated completely the spectral problem in dynamical terms. And here, how you can study this, that's what we discussed last time. The trace map has a first integral, so-called Freaky-Vogt invariant. This is the first integral, and therefore you can foliate the three-dimensional space into two-dimensional surfaces and consider the restriction of the trace map onto those surfaces. The line that we considered entirely belongs to one of those surfaces, and this is the surface that corresponds to zero value of lambda of coupling constant. When you increase lambda, then those surfaces foliate the space. And it turns out that the restriction of the trace map onto one of those surfaces is hyperbolic, which means that there exists a horseshoe that consists of all orbits that are bounded under the action of the trace map on that surface. And that set is locally maximal hyperbolic set, and all other points goes to infinity either under positive or negative iterates. And therefore, you can interpret the spectrum as in the following way. You have the line of initial conditions, you have a horseshoe, you have the intersection of this stable set of that horseshoe with that line, and that's a dynamically defined counter set as soon as you know that you have the transverse intersection. And since we know a lot about dynamically defined counter sets, and since we know how to work with hyperbolic sets, we can establish lots of properties. So for example, you can prove that thickness of the spectrum tends to infinity as coupling constant belongs smaller and smaller. And as a consequence, we get that Hausdorff dimension tends to 1 as coupling constant becomes smaller and smaller. And actually, I want to mention one open problem right away. We know that the transversality that I mentioned, transversality between stable foliation, stable lamination for that horseshoe and the line of initial condition is known for large values of coupling constant and for small values of coupling constant. And we still don't know that the transversality holds for all values of coupling constants. Also, there are some arguments that heuristically show that that should be true. So this is an open problem, and clearly stated, and unfortunately it's not quite clear how to construct that cone field that would prove that. So the heuristic argument that shows that that should be true is the following. Suppose that it is not true. Suppose that you have some points of tangency. Suppose that those points of tangency are quadratic. Then by a small perturbation of the parameter, you should be able to find a quadratic point of tangency between the line and one of the boundary stable manifolds, which means that that point of intersection between the stable set and the line will be just one isolated point. But we know from the spectral theory arguments that the spectrum of the Fibonacci Hamiltonian cannot contain isolated points. And that shows that at least you cannot have quadratic tangencies. Well, you could still have some cubic tangencies, maybe, probably not, but this is an open question. All right, now I'm going to open questions, and the first one is the following. Actually, trace map can be defined for a potential that is given by any substitution, not necessarily by Fibonacci substitution. Remember that all we used in order to define the trace map is the recurrence relation between the products of transform matrices, and since you get that recurrence relation from the fact that the potential is given by substitution, if you get a different substitution, you just get a different recurrence relation, but you still get some recurrence relation. So for example, if you consider period doubling substitution, then it is closely related to the following map of the plane, and the line of initial conditions is also presented there. And if you consider Sumor's potential, then it's closely related to the following map of the plane with the set of initial conditions, which is also written there. So, for example, what does it mean closely related? The formal statement is the following. Let's consider this period doubling trace map. Let's call the point unstable if when you start to iterate that point, then after some moment, the first coordinate is necessarily smaller than 2 all the time. Maybe not immediately, but after some iterates. So that's a definition of the point which is good for us, and all the other points are bad for us. And so the energy E belongs to the spectrum if and only if this particular point on the line of initial conditions belong to the good set of points, the set of points that are not covered by that definition of unstable points. So how does it look in on picture? This is a computer-generated picture, of course. So if you take coupling constant which is equal to 0, then you will get this diagonal line, and you can see that the intersection of that good set with that line must be an interval, and that corresponds to the fact that the spectrum of the free Laplacian is an interval. But then you just shift this line, shifting the coupling constant, you get this line, for example. It's known that this intersection of that set with this line is going to be a counter set of 0 measure. But that's all we know. For example, we don't know whether it's true or not that Hausdorff dimension of that counter set tends to 1 when coupling constant tends to 0, when this line converges to the diagonal. And you have an explicit map, you have an explicit definition of the set. Just try to answer this very simple question. What happens if coupling constant tends to infinity? Can you prove that Hausdorff dimension tends to 0, and how does it tend to 0? So whatever properties one can prove about those intersections, that would be quite interesting. It's not even known formally that what you have here is a nice foliation by smooth curves. You can see that on the picture, that obviously should be like that, but, well, how do you know? It's possible to prove that for the curves that are on the boundary of the gaps. That is not too hard, but for the other curves, it's not totally clear. Similar problem can be formulated for the Sumor's potential. The same definition for unstable set. Different map, different curve of initial conditions. Notice that this curve, nevertheless, is also half line, not a line, but half line, because for a fixed value of the coupling constant, you just have horizontal half line. And this is how the picture looks like. For the 0 value of the coupling constant, your spectrum is just an interval from -2 to 2. When you increase the value of the coupling constant, you get sections of this picture by horizontal lines. Once again, nothing is known about the limits of the Hausdorff dimensions and so on and so forth. Can you prove that Hausdorff dimension must coincide with box counting dimension in this case? Actually, there is another dimension called packing dimension, which is even more relevant from the physical point of view, because that's exactly the one which is responsible for the rate of transport of the wave packets. Do they coincide, all those fractal dimensions in this case or not? So that's all the questions that can be asked. All right. Another class of potentials that we considered is a class of Sturmian potentials, and those look quite differently. Once again, we introduce the class of substitution potentials and to introduce the class of Sturmian potentials. The intersection of those sets is non-empty. For example, the Fibonacci potential belongs to both classes. And actually, not only Fibonacci potentials, there is a class of potentials defined by primitive invertible substitutions. All of them are in these intersections. But nevertheless, there are substitution potentials that are not Sturmian, and there are Sturmian potentials that are not substitution. Nevertheless, Sturmian potentials are related to the properties of the trace maps, and they are related in the following way. So first of all, this is the definition of the Sturmian potentials, just a short reminder. And what's important for me is that alpha, the rotation that corresponds to this class of Sturmian potentials, is fixed and can be represented as a continued fraction expansion. For example, if you consider Fibonacci potential, then it will be just you will have all ones in this continued fraction expansion. I will not explain why this is true. I will just formulate a dynamical problem. Let's consider the following two transformations in R3, U and P. P is really simple. It's just a symmetry with respect to some plane. And U is the Z coordinate is fixed, and you have a family of linear transformations. And then it's easy to check that the product of those gives you exactly the trace map that we studied. Well, now let's define T sub A, where A is a natural parameter, natural number, and T sub A is U to the power A multiplied by P. So this is a composition, and it's possible to prove that for each fixed natural A, you will get a map which has all the same properties as a Fibonacci trace map. So, for example, Freaky-Vogt invariant will be preserved. The restriction of that map to the Kelly-cubic internal part of Kelly-cubic is going to be Pseudo-Anosov homeomorphism. On the surfaces, the map is going to be hyperbolic exactly in the same sense as for the Fibonacci trace map, and so on. So you have a countable number of hyperbolic maps for a given surface. And what you want to know what happens. You have exactly the same line of initial conditions. And what happens is the following. You pick a point on that line that corresponds to some energy, and you start iterating this point by not just by one of those maps, but by the sequence of those maps, which corresponds to the sequence of coefficients in the a continued fraction expansion of that irrational number for the rotation in the family of Sturmian potentials. If the orbit of that, if that sequence that you get in this case is going to be bounded, then energy belongs to the spectrum. If it's unbounded, then energy does not belong to the spectrum. This is the theorem and spirit of another statement that was obtained by Belisard and Quasars in their paper. And there they consider it a little bit different set of generators, but in the spirit it's exactly the same statement. So how one would approach this problem? Let's consider the baby problem, baby model in this case. Let's take a horseshoe, and let's take a neighborhood of that map in the space of diffeomorphisms. And let's take the composition of the maps from that neighborhood. So on each step, we change the map a little bit. Now, what I want to do, I want to consider the neighborhood of that horseshoe and the set of points that will never leave this neighborhood under that process. So you apply one of those hyperbolic maps, but those maps are a little bit different on each step. What will happen is that the set of points that will never leave that neighborhood is going to look exactly as it was for one map. So for one map, it was just the elimination by the stable leaves of the horseshoe. And in this case, it will be elimination by smooth curves. And those curves, I never checked that accurately, but I believe that it's still true. Those curves can be included into C1 foliation, invariant in the sense of that composition. And therefore, the situation is very much similar to what you see for application of just one map. So I believe that can be proven just by graph transform techniques. At least the existence of the stable curves definitely can be shown by graph transform. Just let's consider dimension 2, because that's our setting. In our setting, we have only in dimension 2, certainly. So in our setting, we have all those maps defined on the surfaces. So that's in terms of dimension, I'm not cheating. All right. So how does it apply to our composition? In our case, we have countably many hyperbolic maps. Those maps are not necessarily close to each other, but if they have joint family of invariant cones, then maybe similar statement holds. And if this is true, then the set of points that never leaves some bounded domain under such composition is going to look like the foliation by smooth curves locally looks like a product of interval by a counter set. And then you have some line of initial conditions. So the intersection must be a counter set of zero measure, also not necessarily dynamically defined counter set. So for example, it is true for such a set that Hausdorff dimension is independent, locally independent of the point. But it's not true, for example, that Hausdorff dimension must coincide with box counting dimension. It's not necessarily true that box counting dimension for this counter set coincides with Hausdorff dimension. It's not true, for example, that Hausdorff dimension is necessarily smaller than 1. It could be equal to 1, and so on and so forth. So there are some properties that are inherited, and there are some properties that do not hold. So why is it interesting? First of all, if this is true, if that construction works for that family of maps, then we would prove the following conjecture. So take two classes of Sturmian potentials given by two irrational numbers, and suppose that those two irrational numbers are similar to each other in a sense that only some initial parts of the continuous fraction expansions are different, and the tail is the same for both of them. Then that construction would imply that the spectra for those two families, well, are not necessarily the same, but they must be diffeomorphic. So there is a diffeomorphism of a neighborhood of one spectrum that sends it to another spectrum. And therefore, all the reasonable properties in terms of fractal dimensions and so on must be preserved, must be the same. And if this is true, then that would imply the affirmative answer to the following long-standing conjecture. The long-standing conjecture is the following. Consider Hausdorff dimension of the spectrum of the Sturmian potential. The conjecture is that this Hausdorff dimension is constant for almost all rotation numbers alpha. This conjecture comes from the initial works by Belisar, so it's more than 20 years old, and it's still open. So why would it follow? The previous conjecture would imply that the Hausdorff dimension of the spectrum as a function of alpha is invariant under the Gauss map. So what is a Gauss map? You just take the continuous fraction expansion and you forget the first element. And this previous conjecture just tells that in this case Hausdorff dimension doesn't change. So the Hausdorff dimension gives you the function, measurable function, which is invariant under the Gauss map, and therefore by ergodicity that implies that for almost all alphas that should be just the same constant, because the measure which is invariant for the Gauss map is absolutely continuous with respect to the Lebesgue measure. So once again, this is a strategy, but it would be nice to actually implement it and to make it work. All right. What is known about spectral properties of Sturmian Hamiltonians? For example, it's known that whatever alpha you take, at least for large enough coupling constants, the Hausdorff dimension is positive. But it's also known that this Hausdorff dimension is not necessarily smaller than 1. It's smaller than 1 if and only if you have that condition on the sequence of elements of the continuous fraction expansions of the rotation number. And notice that, once again, we know that that condition holds for almost all irrational numbers, but definitely not for all. It's easy to give an example when that lim_inf is equal to infinity, and then Hausdorff dimension is equal to 1. And therefore, that's another explanation that in this process, if that strategy works, you can get something which is not a dynamically defined contraset. Another result, quite recent, is the following. I just extracted one particular example from that result. They proved much more. Liu, Wen, and Pierre proved the following. Consider the Sturmian potential that is related to beta, to some rational number, such that in the continuous fraction expansions, you have only 1s and 3s, but the numbers of so you start with 1s, you get some 1s, then you get 3, 3, 3 for a long time, then you choose very long time when you get only 1s and so on. So you just have some weird number, weird in terms of continuous fraction expansion, but explicit. In this case, they managed to prove that Hausdorff dimension is strictly smaller than the upper box counting dimension. And once again, that shows that in this case, the spectrum is certainly not the dynamically defined contraset. No. 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 Okay. All right. Essentially, that's the problem that I wanted to mention. And now I'm turning to the next topic. Let's ask the following question. So yes. No, well, that's definitely not true, as this example shows, for example. I don't think so. So what is known? It's clear that if, for example, you have eventually periodic expansion, continuous fraction expansion, then you probably get, well, not probably, definitely get the dynamically defined contraset as a spectrum. Just because what happens, you iterate the line of initial conditions several times, and then you can just take the composition and iterate that composition over the period. And then it's dynamically defined, because any composition of those maps is going to be hyperbolic. It's going to be one of those maps again. Okay. All right. So now let's ask the following question. We have a spectrum of an operator in the Hilbert space, L2Z. But what we can do, suppose that you are trying to calculate the spectrum on a computer. You definitely cannot work with a Hilbert space. You have to work with a Euclidean space. So what you do, you take a long box, a long interval, and you just put, say, Dirichlet initial conditions, and you forget everything else. So you have just a matrix, finite matrix, and then you calculate eigenvalues of that matrix. And you say that those eigenvalues give you some approximation of the spectrum of the operator. Well, if you are not satisfied with the way the approximation goes, you can take the bigger, the larger interval and do the same. Well, natural question, will you have a convergence in some sense of the spectra of those finite dimensional operators to the spectrum of the actual operators that you study? So in other words, you can formulate it either in terms of measures or in terms of distributions of those measures. It doesn't matter. So, for example, in the definition which is written there, it's formulated in terms of distribution functions. Let me try to explain it in terms of measures. Maybe it's easier. So let's take. So the answer is yes. You will have a convergence, and this is how it goes. Take this finite dimensional operator, this matrix. Take the set of eigenvalues, and put a probability measure, which is atomic measure, that sits on the eigenvalues of that matrix, equidistributed on the eigenvalues. So you just put, if you have n eigenvalues, you put 1 over n delta function delta measure into each eigenvalue. Then when you send the size of the matrix to infinity, then the sequence of those atomic measures will be weakly convergent to some probability measure, and that measure will be supported on the spectrum of the initial operator. That measure is called density of states measure, and the distribution function of that measure is called the integrated density of states, and this is how it is defined. So what is known about integrated density of states? First of all, it is known that the support of the density of states measure is necessarily the spectrum. So as I said, that measure is supported on the spectrum of the operator. And it's also known that in one-dimensional case, the integrated density of states is a continuous function. In other words, the density of states measure doesn't contain any atoms. So, for example, let's consider free Laplacian. So our potential is just 0. In this case, the integrated density of states is going to be given by this function. So the graph of this function will be, so it's 0 up to -2. It's 1 after 2, and it's a function of this form somewhere in between. So this is a nice smooth function everywhere except the boundary points of the spectrum, and in those points you have infinite derivative, and the function is Euler continuous with Euler exponent 1/2. So what does it mean and why it's important? Let's now do that procedure that we did. We take finite approximation, we consider eigenvalues. It turns out that those eigenvalues will be distributed with respect to the measure with this density. So in a sense, you will get more eigenvalues closer to the boundary points of the spectrum and less eigenvalues inside, but still you will get some non-zero fraction of those eigenvalues in each part of the spectrum. So that explains why integrated density of states is physically more relevant than the spectrum itself. And so we want to know something about density of states measure, well, not only for free Laplacian, but also for our potentials that we study for one-dimensional quasicrystals. It turns out that it is related closely to the measure of maximum entropy that sits on the horseshoes, invariant horseshoes for the trace maps. And this is how the relation goes. First of all, let me remind you that for the free Laplacian, we can think about the free Laplacian in the following way, about the density of states in the following way. You have this hyperbolic map of the torus, and you have a semi-conjugacy between this torus and the internal part of the Cayley cubic. And on the line of initial conditions that connect this point and that point, you have that density of states measure that is given by this density. And it turns out, and it's a simple calculation since you have an explicit form of the semi-conjugacy, that if you take just a Lebesgue measure on this line and send this Lebesgue measure under this semi-conjugacy there, what you will get is exactly the density of states measure for the free Laplacian. So in a sense, in the coordinates on the torus, the density of states measure for free Laplacian is just a Lebesgue measure. Well, it will be convenient to me to think about the Lebesgue measure on this line in a little bit weird terms. Namely, I will take this rectangle, which is an element of the Markov partition for the linear transformation of the torus. I will take the two-dimensional Lebesgue measure on this rectangle, and then I will just project that measure along the stable leaves of the linear transformation onto this line. Well, certainly I will get a Lebesgue measure on that interval, but that representation survives after I switch on the perturbation, because when I switch on the perturbation, I still get a Markov partition. I get a measure which is inherited from the Lebesgue measure to that new Markov partition, and that measure is certainly the measure of maximum entropy. That's the only measure which is invariant under the topological conjugacy. And then I can project that measure of maximal entropy onto the line of initial conditions along the stable manifolds of the horseshoe. That will give me exactly the density of states measure for the Laplacian for non-zero coupling constant. So this is a formal description of exactly this process. So this lemma just says that if you take the Lebesgue measure on that line, it will be sent to the density of states measure for the free Laplacian. And this statement claims that when you change the coupling constant, then what you can do, you can just project the normalized measure of maximum entropy on that element of the Markov partition along the stable manifolds to the line of initial conditions, and you will get the, roughly speaking, the density of states measure, well, adjusted with respect to the parameterization of the line. Why this is true? Because you can characterize the measure of the density of states measure in the following way. Suppose that you have a family of measures that have the following properties. First of all, for zero value of the parameter, let me remind that this picture is a picture of a spectra for different values of coupling constants. So for zero values of the parameters, I want to get the measure which is integrated density, which is density of states measure for the free Laplacian. Then I want the family of measures to be continuous, continuously dependent on coupling constant. I want the support to be exactly equal to the corresponding spectrum. And moreover, as soon as two gaps were opening, I want the measure of this interval to be exactly equal to the measure of this interval. Because density of states measure, integrated density of states on the gaps of the spectrum must be equal to constant, and that constant is not going to change when you change the parameter in such a way that the gap does not disappear. And if you get the family of measures that satisfies those properties, that necessarily is a family of density of states measures. And since the family of measures that you get by those projections do satisfy this property, then automatically you get that that's exactly the set of density of states measures. And so since when you split the Lebesgue measure on the element of Markov partition into those rectangles, you exactly split it in such a way that you get a measure of maximum entropy, that's exactly the one that will inherit all those properties. So why is it useful? What does it give you? For example, there exists a gap labeling theorem, not necessarily for Fibonacci Hamiltonian for large class of Hamiltonians, but for Fibonacci Hamiltonians, a Hamiltonian looks in this way. So what does it mean? If you have a gap in the spectrum, then the integrated density of states must be constant on that gap. You may have at most countably many gaps. For Fibonacci Hamiltonian, you actually do have countably many gaps. And so the values that integrated density of states can take on those gaps is necessarily at most countable set. So what is the set? It turns out that the set of possible values can be described from some algebraic reasons. And in the case of Fibonacci Hamiltonian, this is exactly this set of points on the interval from 0 to 1. And this is a dense set of points, but not all points on the interval are there. And it's possible to prove that all the gaps that are allowed by the gap labeling theorem are actually open in the actual Fibonacci Hamiltonian. So it's known as Drayton-Martini problem to prove that all gaps allowed by the gap labeling theorem are open. So 10 Martini problem usually formulated for the almost Massieu operator. And for that one, 10 Martini problem means to prove that the spectrum is a Cantor set for all values of the coupling constant. The Drayton-Martini problem is not only to prove that the set of gaps is dense, but also that each gap which is allowed by the gap labeling theorem is open. And so for the Fibonacci Hamiltonian, this is indeed the case. And how is it related to the dynamics of the trace map? Let me go back to this picture. we know that the gaps are open exactly where stable manifolds that starts in the singularities of the Kelly cubic intersect the line of initial conditions. But if you take the set of, so what points on the torus correspond to singularities? This point, this point, this point, this point, and others. So you have those 4 points, and you have lines that are exactly lines in the direction of the stable eigenvalue. And you know exactly the inclination of those guys, and you know exactly where those lines intersect this line of initial conditions. And it turns out that that's exactly the set of points prescribed by the gap labeling theorem. And you know that for each of those intersections, as soon as you switch on the coupling constant, the gap is opening. And that's all. So you know that all of those gaps are necessarily open. Another consequence. Last time we discussed that all the gaps on this picture opens linearly. So the speed of converging of the gap in the spectrum to 0 with lambda is linear in lambda. And we discussed that that limit must necessarily be dependent on the family of gaps that you choose. But now we have labels for the gaps. And so we can say something, we can try to say something about that limit in terms of that label. And it turns out that you can actually do that. And you can prove that this limit is, roughly speaking, 1 over the absolute value of the label. And here's how the proof goes. Once again, let's return to this picture. You know that the gap opens linearly because the distance between two periodic orbits that are born from singularity is going to open linearly with lambda. But now you have strong stable manifolds, well, they go in this direction, strong stable manifolds, and those manifolds are very close to the strong stable manifold that corresponded to the unperturbed system, the one that goes through the singularity. Now you know exactly the contraction that you get under the inverse of the map, and you know that if the label is large, then you need to apply your map several times in order to reach that point of the intersection. And so you must contract that gap, and you know, roughly speaking, how many times in terms of the value of the label you have to get that contraction. And that gives you exactly the coefficient in that limit. So if you do that accurately, it turns out that that coefficient can be bounded from above, but unfortunately not below, since the semi-conjugacy is really bad near the singularities. But if you consider only gaps that are away from the boundaries of the spectrum, then actually this constant can be also bound away from below. So certainly not, because we know that the sum of the lengths of the gaps is finite and the harmonic series diverges, so it cannot be uniform. Another property that one can prove just using the dynamics of the trace map is Hölder continuity of the density, integrated density of states. Then integrated density of states must be at least log Hölder for any potential. But for many potential, you can prove more, and usually people expect Hölder continuity with Hölder exponent not greater than 1/2 and not greater exactly because for the best possible case for the free Laplacian it's just 1/2. So the paper where initially that was shown that you have Hölder continuity with exponent close to 1/2 for almost Monsieur operator appeared in annals, so that was a big deal. So for Fibonacci Hamiltonian, we can also show that, and we can formally show that you actually have convergence of the Hölder exponent to 1/2, and that's exactly the best that you can expect. Okay. Now, a simple corollary of the fact that the density of states measure is just a measure of maximum entropy projected to the line of initial conditions is the fact that it is exact dimensional. It's known that any hyperbolic measure is exact dimensional. For two-dimensional case, it was shown by Lysen-Young and Ladrapier, and it was a big conjecture, Ekman-Reuel conjecture, to prove that for general case for higher dimensional situations, and that was done by Basin and Quasers later. But in our case, it's enough to use that Young-Ladrapier result, and we know that our measure is exact dimensional. So it means the following: if you take generic point with respect to that measure and consider the measure of small epsilon neighborhood, then the measure should be of the order epsilon to some power, and that power is the same for almost every point, almost every in terms of that measure. So that's exactly what's written here, and d sub lambda is that power. Interestingly enough, that this is the first family of ergodic Schrödinger operators where exact dimensionality of the density of states measure was formally shown. So it's just something that you don't know how to approach using the methods of spectral theory, and dynamical methods gives you that almost for free. Also, you can prove the convergence of that exponent to 1. When coupling constant tends to 0, which is interesting to compare with this result, because this result is exactly the same property, but formulated not in terms of almost all points, but in terms of all points in the spectrum. And it turns out that if you want that to hold for all points in the spectrum, then you cannot do better than 1/2. And you are much better if you care only about almost all points. Another strange property that holds here is that this exponent, it's known that it's certainly bounded from above by the Hausdorff dimension of the spectrum, but in this case it's strictly smaller than the Hausdorff dimension of the spectrum, and it's also, for people working in spectral theory, it's also was a very unexpected result, because that's exactly the dimension of the density of states measure that defines and gives you limits for the rate of transport of the wave packets. And people use Hausdorff dimension of the spectrum because it's just an upper bound. That's the best they could find. And it was expected that those quantities do not coincide, and it was a conjecture, and it is a conjecture by Barry Simon that they do not coincide for the class of potentials. But this was, once again, the first potential where it was possible to prove that formally. So how one can extract that from the dynamical properties, from the relation with the measure of maximum entropy? We're going to use two results, one by Manning and another by Manning and McCluskey. The first one claims that there is a relation between Hausdorff dimension of the hyperbolic measure, Lyapunov exponent with respect to that measure, and measure theoretical entropy of that measure. So once again, you have a horseshoe for axiom A diffeomorphism of a surface. That's exactly our case. You take any hyperbolic ergodic invariant measure, and you have this relation where this is the Hausdorff dimension of the measure, which is exactly that exponent that we had on the previous slide. This is the Lyapunov exponent in the unstable direction with respect to this measure, and this is this is the Hausdorff dimension of the measure restricted to the unstable leaf, and this is the entropy of that measure. The second result that we will need is the relation between the Hausdorff dimension of the spectrum and the pressure of the log of the expansion rate along the unstable manifold. So the claim is the following. Let's consider the minus log of expansion along the unstable leaves, and let's consider the pressure that corresponds to this potential, delta multiplied by this function. So when you change delta from 0 to 1, you get a monotone function that necessarily, the graph necessarily crosses the horizontal line. So there is only one root, and it turns out that that root, that delta, is exactly the Hausdorff dimension of the unstable Hausdorff dimension of the horseshoe. So how can you use both of those guys? First of all, variation principle claims that the pressure with respect to the potential is supremum of the sum of the integral of the potential and the measure theoretical entropy of that measure over the all invariant ergodic measures. And then let's see what happens. If M is a measure of maximum entropy, then and delta is an unstable Hausdorff dimension, then by the previous theorem we know that 0 is exactly the pressure for this potential, which is by variational principle is given by the supremum. But since it's a supremum for over all the invariant measures, it's not less than the sum for the measure of maximum entropy. And this is equal to that sum where we can replace the measure theoretical entropy with respect to the measure of maximum entropy by just a topological entropy, again by variation principle. And this is just a Lyapunov exponent with respect to the measure of maximum entropy. So by the Manning theorem, we know that the dimension of the measure of maximum entropy is exactly this ratio of the entropy of that measure and Lyapunov exponent of the measure of maximum entropy. And from here, we know that it's not greater than the Hausdorff dimension of the horseshoe along the unstable leaves. And that's exactly the bound of that quantity by the Hausdorff dimension of the spectrum. But on the other hand, from here, we can immediately see when the equality happens. Equality happens if and only if you get equality here. And equality at this place, you get if and only if the measure of maximum entropy is exactly the equilibrium measure with respect to this potential. And there is unique equilibrium measure for a given potential. And that uniqueness implies that all we need to check is that the measure of maximum entropy is not an equilibrium measure for this potential. But we know that two equilibrium measures coincide if and only if the potentials are cohomological, and the potentials are cohomological if and only if. So we want this potential not to be cohomological to the constant potential. The constant potential corresponds to the measure of maximum entropy. So all we need is just to check that this one is not cohomological to a constant potential. And in order to check that, it's enough to check that the average multipliers over all the periodic orbits are not all the same. And for that, you just take two explicit periodic orbits of the trace map and check explicitly that the average multipliers are different. And that's all. So you prove the strict inequality between those quantities. Oh well, it looks like I'm out of time. So let me stop here, and I will say a couple of words about the integrated density of states for higher dimensional case next time. Yes, that's exactly what I mean by the Hausdorff dimension of the measure. So if you have a measure, that Hausdorff dimension of the measure is just a Hausdorff dimension of the set of generic points. Not the support of the support of the measure here is in our case the spectrum itself, and we want to show that this one is exactly smaller than the Hausdorff dimension of the spectrum.